Hello! Today we are going to be going over Chapter 14 so that you are prepared for your Chapter 14 quiz, which is in 2 days on Thursday. Alright, so remember Chapter 14 is all about solids, liquids, and gases. Before I get started, I want to say you should really study the Chapter 14 review questions and the Chapter 14 homework assignments that I gave you and that I corrected yesterday in the Chapter 14 homework corrections. Those are going to be very helpful for you for the quiz. So, alright, let's go over this and then you will have time to study with whatever remains of the period when I'm done. Alright, so 14.1 was about matter and thermal energy. Remember, we have gone over these 4 facets of the kinetic theory a million times, but you do need to know these 4, and you need to remember that the kinetic theory is an explanation for how the particles behave. They tell us how particles of substances, whether that's atoms, well, all we really have talked about is atoms, how atoms behave. Remember that the 4 facets are that all matter is composed of tiny particles called atoms. All atoms have energy associated with them. This energy causes the atoms to be in constant and random motion, and the more energy that the atoms have, the faster they move. The vocabulary that you need to really make sure that you know is volume to start. Remember, volume is the measure of the amount of space a substance takes up. It's a measure of liquid and gas, but it can also be a measure of solids. We have many different units for volume, and I gave you some examples here: 10 milliliters of water, 1 liter of air, gaseous air, etc. The next vocab word is mass. Remember that mass is the amount of matter in a substance, and we can measure mass of solids, liquids, and gases. We have lots of different units that we can use. And then we have density. Density is mass per amount of volume of a substance. So the amount of mass, so for example, grams, in an amount of volume. For example, milliliters. That's our most common unit that we'll see, grams per milliliter. But it doesn't have to necessarily be that. Remember, we talked about density a lot when we were talking about gas particles. We talked about it with all 3 of the states of matter. Remember, we said that solids are very dense. They're right next to each other. Oh, that's tiny, too small. They are right next to each other, all compact, right? So there's a lot of matter, there's a lot of mass in this volume of space. Whereas a liquid, in the same volume, those particles are a little bit more spread out. So it's less dense than a solid. And a gas, there's a lot of space between the particles. So this one would be the least dense. So this would be most dense, medium dense, and least dense. All right. Okay, and then finally, our last vocab word we talked about was this idea of pressure, but we talked about this a lot more later on in the section on special properties of gases. 14.3, I think it was. So we will get, you do need to understand what pressure is, but we go over this much more in 14.3. Remember that it's a force exerted by a substance per unit area of another substance, and that actually makes sense because remember, pressure is equal to force divided by area. It's a measure of gas, and mostly only gas. We will use units of atmospheres, millimeters of mercury, pascals, and kilopascals. Those are all units of pressure. And remember that gases exert a force, aka a pressure, on the wall of the container that holds the gas, and they exert a force onto each other. This is what creates pressure. This is what creates pressure. All right, then we talked about our states of matter. Our 3 states of matter, well, we have 4 states of matter. The first one is solid, and matter can exist in any of these 4 forms. And if we change the conditions, like the temperature or the pressure, we can change the state of matter. And we're going to learn that probably in chemistry when you get there, how that happens more. So, but you could also understand how it happens. If I increase the temperature enough, I'm going to give these particles enough. If I start with a solid and I increase the temperature enough, I'm going to give those particles enough energy that they become a liquid, that they break away from each other and they start moving a lot quicker. And if I give those liquid particles enough energy, they can break off away from each other and turn into a gas, right? These are our phase changes. So matter can exist in any one of these forms, given... And we can change those forms based on changing how we change the pressure, the temperature, the energy associated with them. All right, so remember, solids are made of particles with very low kinetic energy, and they move very little. They're actually only vibrating. They don't move the way that liquids do. They don't move past one another the way that liquids and gases do. The attractive forces between the particles of a solid are very strong. They have a definite shape. Remember, this is not going to change shape. If this is a solid, whatever, carbon or whatever this is I've drawn here, it's not going to change shape if I hold it with my left hand or my right hand. If I put it in a square container or a circular container, it stays this shape. And its volume is also definite. It's not going to change. The volume is not going to change either. Like I just said, density of solids is higher than it is for the other states. And for liquids, it's made of particles with medium kinetic energy, so they have a little bit more kinetic energy associated with the particles than do solids, but not as much kinetic energy as gases have. The particles move past one another and collide with one another, and they collide also with the container that they're held in. The attractive forces are medium. They're not as strong as in a solid, but they're not as non-existent as with a gas. The shape is indefinite. Remember, if I put this amount of water in this little cup, it will take the shape of the little cup. If I put it in this tall cup, it will take the shape of the tall cup. If I put it in this fat cup, it will take the shape of the fat cup. But the volume is definite. The volume stays the same throughout. This is 15 milliliters of water. This is 15 milliliters of water. This is 15 milliliters of water. The volume is definite. The shape is indefinite. And the density, it's more dense than gas, but not as dense as solids. So medium density. Then we have gas. Gas is our third state of matter. Gas particles have the higher kinetic energy than do liquids or solids. The particles collide with one another and the container, and this is what creates pressure. There are no attractive forces, or they're very, very small. We say basically no attractive forces between gas particles. So these are what's called, when they collide with each other, they have an elastic collision, meaning they run into each other and they bounce off perfectly. There's no sticking and sliding around each other like with liquid particles. The shape is indefinite and the volume is indefinite. Remember, gases will take the shape and the volume of the container that they're in. So the shape of this gas is a cube, but if I put it in a spherical container, it would take the shape of a sphere. If I put it in a triangular container, it would take the shape of the triangular container, etc. So the shape of the gases are indefinite. We can change the shape based on the shape of the container. We can also change the volume of the gas, right? Remember, the gas will occupy the entire container that it's held in. The gas particles aren't going to just stay. If we have, look, I'm drawing with black right here. Look here. If we have 10 black gas particles, they're not just going to stay in this corner, right? Maybe they start there, but eventually they're going to spread out until they are all evenly dispersed throughout this container, and they will take up the entire volume of this 15-liter container. They'll take up the entire volume of the 5-liter, the entire volume of the 1-liter. They spread out evenly throughout the container. So this is why we also say that the volume is indefinite with gases. All right. Our fourth state of matter is plasma. Remember that plasma is matter that has high enough energy to overcome not only the attractions between the atoms, like how gas has enough kinetic energy to overcome the attractions between the atoms, but plasma has enough, it gets so much kinetic energy that not only are the atoms not attracted to each other, but it actually breaks up the electrons from the atom. So we have it breaks up the atoms into its subatomic particles, or into its particles, which are actually smaller than it, obviously, the subatomic particles, meaning the particles that make up the atom. So we have these electrons breaking off from the atoms in a plasma state. Obviously, this is going to have the highest kinetic energy of all four states. That's something you should obviously be able to explain and understand. It has the highest kinetic energy. All right, moving on to thermal energy and temperature. Remember that thermal energy is the kinetic energy and the potential energy of atoms. It's all of the energy in a substance's particles. So all of the energy associated with all of the particles of a certain substance at a certain time. The temperature is the average kinetic energy of the particles that make up that substance. What we can do is we can cause state changes or changes in state of matter. We can add or take away thermal energy, meaning we can add or take away thermal energy from from a substance that's in one state, and we can cause it to have what's called a phase change. We can cause a phase change. We can force a phase change, which is a change from one state of matter to another state. We need to be able to draw this phase change schematic, which you had to, not on over here, it's on the next page, I guess. You needed to do this in your homework from yesterday, and I drew it yesterday. So this is our phase change schematic. There are 8 different phase changes that we need to be aware of, and we're only doing these phase changes with our three types of matter. We're not including plasma in this. So we have solid going to a liquid, which is melting, liquid to a solid, which is freezing. Then we have liquid and gas. The phase changes here are vaporization, when we're going from liquid to gas, and condensation, when we're going from gas to a liquid. Then we have the weird ones between solids and gas, when we're going from a solid to a gas. What has to happen here? We totally skip the liquid phase. We just go straight from the solid to the gas phase. So that means we have to add a ton, huge amount, very quickly, of kinetic energy very quickly to a solid in order to sublimate it, or to cause sublimation and force it to become a gas, right? So we have to add a huge amount of kinetic energy, because a solid has very, very low kinetic energy associated with it, thermal energy associated with it, and gases have really super high thermal energy associated with them. So if we want to do the opposite, go from a gas to a solid, what would we have to do? We would have to take away all of that kinetic, not all of it, but most of that kinetic energy from the gas very quickly, very rapidly, and cause deposition and cause it to go to a solid. So we make the gas very cold very quickly. So we completely skip the condensation phase and just go, or the condensation phase change, to a liquid. And then we go just directly from a gas instead to just straight to a solid, not going to a liquid first. You also need to be able to draw a phase change diagram, which is a graph that shows the conditions that are necessary for different states of matter for one substance. So I will give you, like I have been giving you, a freezing and a melting point, and a vaporization and condensation point, and various temperatures and various amounts of energy, and you'll need to correctly draw and label a phase change diagram. If you don't know how to do that, I would strongly recommend going back to the lecture where we did that. This was in 14.1, the first lecture from 14.1. All right, so that was it for 14.1, I believe. Yep. Okay, so remember really quickly about phase change diagrams or graphs here. They are all going to have the same shape. So there's going to be 2 lines like this and 3 angled lines between them. And the solid is always going to be this line, the liquid is always going to be this line, the gas is always going to be this line. The only thing that changes is the temperatures and the amounts of energy that you have to graph. So the graph will look differently based on these values that I give you. All right, 14.2 is about the special properties of liquids. Remember, we started with buoyancy. We said that buoyancy is the ability of a liquid to exert an upward force on an object that's immersed in it. So there is a force pushing up on the ship, we know that, and the opposing force is the weight of the boat, or the force of gravity pulling down on the boat. The opposite, this opposite force of that, this is the buoyant force pushing back. Remember that Newton's third law says that for every action there is an equal and opposite reaction. So because of that, we have the force of gravity, or the weight of the boat pushing on the water. We have the buoyant force pushing up on the boat. Archimedes' principle. Archimedes was a guy, just some guy, in the 3rd century that made a discovery regarding buoyancy. That's how it got its name. It was named after Archimedes. So I give you the 3rd century to just let you know this is a really old concept. He found that the buoyant force on an object is equal to the weight of fluid displaced by that object. So remember, I would listen very closely. You should definitely understand the Archimedes principle problems that we went over in the homework corrections yesterday. You should definitely understand those, because you will see an Archimedes principle question where you have to determine the buoyant force or the weight or whatever it is. You're going to have to be able to solve those for your quiz on Thursday. Remember that weight is also called the force of gravity. It's W equals mg. You might also see this written as Fg. Force of gravity is equal to mg. So the weight of the water displaced by the object is equal to the buoyant force acting on that object. This is equal. So Fg is equal to Fb, which is buoyant force. This is the weight of the water. Fg of water, or weight of water. Remember, weight is not the same thing as mass. Weight does not equal mass. That's a very important thing that you need to understand, because some of you, not calling you out, but some of the gentlemen in this class still think that weight is equal to mass, and it is not. Weight is equal to mass times force of gravity. Mass is how many kilograms something is. We use weight differently, the word weight differently in science than we do in non-scientific settings, right? I say my weight is 80 kilograms, but my mass is actually 80 kilograms, okay? My weight is in newtons. I don't know what my weight is. I'd have to figure it out, multiply it. Multiply 80 kilograms by 9.8 to figure out my weight in newtons. All right, you've been warned. I will have no mercy on you on the quiz for confusing weight and mass, because I'm telling you a million times, making a big point. They're not the same thing. Do not say they're the same thing. Don't say they're the same thing. Don't say they're not the same. Whew. Okay, finally, the third property of water that you need to be aware of that we talked about is this idea of viscosity. Viscosity is how well a liquid flows, or how thick and sticky the liquid is. So the example I gave you is water. It has a very low viscosity, as opposed to ethyl alcohol, which is the least viscous, the lowest viscosity, even lower than water. It's super thin, not thick, very thin and runny. And the highest, or not the highest, but something that has a very high viscosity is honey, right? It's very thick. It does not pour very easily. So remember, in order to increase viscosity, to decrease viscosity, to make something flow better, to make a liquid less sticky / flow better. Okay, so to make it more runny, you could say, there's lots of different ways that you can say this, we have to increase the temperature of the liquid. So as I increase the temperature of the honey begins to flow more easily. The internal friction of the particles of a liquid is what affects the viscosity. If we have very high friction of particles, we have very high viscosity. If we have very low friction between particles, we have very low viscosity. That's what determines the viscosity. And fun fact, you don't have to know this, but in case you're wondering, there can be this internal friction that I'm talking about. This is actually caused by the shape of the molecules that make up substances. So molecules, we have atoms, which are individuals like this. And there's there's different sizes, different, not really shapes. Yeah, there's different sizes. We'll say different sizes. And in this example, I'm going to say there's even different colors, but there's not really a different color of atoms. So these are atoms, but what can happen is atoms can join together to form what's called, let me draw them out. There. They can join together in a special way to form this thing called a molecule. So what causes the internal friction in a liquid is the shape of the molecules. If we have very big, huge, I've drawn this is a super simplified version of a molecule, okay? Molecules can be massive. They can be, massive. Not really that massive, but we can't see them with our naked eye. But for example, this is an example of a molecule. Oops. Yeah, so something, and then these are all carbon atoms, carbon, hydrogen, 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 hydrogen. All right, you get the point. So molecules can be not just little spheres stuck together. They can be big, huge, long, complex. This is actually a really simple molecule, what I've drawn here. This is called a hydrocarbon, in case you're curious. It's a very simple molecule. It's a chain of carbon and hydrogen atoms together. And these actually, there can be a lot of friction. If we have many molecules that are zigzagged like that, and I have them all together in a liquid like this, do you think these will slide past each other very easily? No. There's a lot of friction there between those molecules, right? There would be a lot of friction. They would rub up against each other. All those extra hydrogens on the outside, or the ends, are going to smack into each other, right? And we're not even talking about molecules that are not only zigzags, but let's say they have zigzags on them already, they like within the hydrogen or within the molecule. So this is one shape of one molecule, like this. So let's say that's one molecule. Do you think this one would have more or less friction if we had a whole substance made of this type of molecule? If we had lots of these molecules, if they were all in some liquid form, there's going to be way more friction between them because they have way more. And this is also 3D, not even talking about the 3D aspect of the molecules. These are not all 2D, right? So, meaning, point being, what causes this friction, if you're curious, what causes this friction is the shape of the molecules. And the more complex the shape, the more friction there's going to be. If there's more friction, there's going to be more viscosity in the substance, in the liquid. Okay? All right. So then we got to 14.3, and this was about behavior of gases. And this is where we talked about pressure, Boyle's law, and Charles's law. Remember that pressure, that has the units of kilopascals or pascals or atmospheres. Pressure is the force exerted per unit area. It's this equation. Pressure in pascals. We must put this in pascals when we're using this equation. Pressure is equal to force in newtons divided by area in meters squared. P equals F over A. Pressure is, remember, caused by gas particles colliding with one another and with the objects, either around the gas or that contain the gas. And these are some examples you're going to need to be able to solve for. You're going to be able to need to use you're going to need to use this pressure equation in order to solve problems about pressure, force, and area. Remember, some of you wanted me to talk about altitude. Remember, altitude is just how high up you go in the atmosphere. And I've drawn this, remember this picture here. So if I have a valley, if I have sea level, okay, it was the top of the mountain, sea level is 2, and then this valley at the bottom. So the blue represent the particles. As we go up in the atmosphere, we go up in altitude, right? As we go up in altitude, the air pressure decreases. Some way to remember this is, think about when you're going up in an airplane. You start at sea level, if you're leaving from Nouakchott, and you go up, 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 way high, 30,000 feet in altitude. Once you're up there, or when you're going up there, your ears may feel like they're kind of popping a little bit, right? They don't feel like they're getting plugged, but maybe they feel like some pressure is being released when you're going up. And maybe you don't even notice that when you're going up. But when you've gone up and you've flown over to wherever you're going, Morocco, and you start your descent to land back down on the ground, you feel it then. Your ears feel like there's something pushing in on your ears. And the reason for that is because you were at a high altitude and a low pressure. I'm going to write that. High. Who has their phone on in my class? It's funny because it was my phone. Altitude. Low. Okay, now it's just annoying. All right, at the top up here, when you're up in the airplane. Oh, I cannot draw an airplane. That's just I don't know what that is. It's not that bad. Maybe it needs a tail. And okay, it's not so bad. All right, so when you're up super high, think about the mountain. We're up super high. We're in high altitude. We're at low pressure. But then when we go down here, we're at low altitude, which is a higher pressure. And the reason for that is because, where's my pointer? There we go. We have less gas particles up here. And as we go down, our gas particles increase. Remember that the gas particles are what causes the pressure. So if I have more particles, I have more particles running into one another. Therefore, I have more pressure. If I go down even further into a valley, somewhere below sea level, like where I live in Washington State is below sea level. So, or at the bottom of the Grand Canyon, for example, below sea level, right? It doesn't have to necessarily be a valley. There's lots of places that are below sea level. Louisiana, the whole state is basically below sea level. Not really, but anyway, we have even higher pressure at an even lower altitude. Okay, so if we start at sea level, we have an atmospheric pressure, it's called, of 1 atmosphere or 101.3 kilopascals. As we go up, this goes down. The pressure will go down. As we go up in altitude, pressure goes down. As we go down in altitude, as we get closer to the Earth, our altitude goes down, but our pressure increases. And if we go even lower, down into an area that's below sea level, our pressure will increase even more. So this is a concept that you need to understand for your quiz. We did lots of examples. I'm not going to go over examples right now of pressure or Boyle's law or Charles's law. I'm just explaining it. So remember, Boyle's law states that at constant temperature, so when temperature remains the same, there's an inverse relationship between volume and pressure. So as volume decreases, pressure increases. If example 1 and 2 here, I start with 1 liter and I go to 0.25 liters. I have I'm decreasing in my volume, therefore my pressure is increasing. Right? Remember, pressure is just collisions between gas particles and between gas particles and their containers. So gas particles in the container, this would be the balloon here. So if we decrease the space that the gas particles have to roam around in, or so to say, we increase the pressure. It's the same concept as, I already gave you lots of examples of this, with the students in the cafeteria versus students in one classroom versus students in the bathroom, right? So as we decrease the volume, we increase the pressure. Or as we increase the volume, we decrease the pressure. This is the equation for Boyle's law that you will need to be able to manipulate and use for your quiz on Thursday. You need to be able to do practice problems with using Boyle's law as well. And then Charles's law is the second law that you need to understand. And Charles's law states that at a constant pressure this time, there is a direct relationship between temperature and the volume of a gas. So as temperature increases, so does volume. Or as temperature decreases, so does volume. As long as pressure is constant, pressure remains the same. You need to be able to use, manipulate, understand Charles's law, which is here, VI over TI equals VF over TF. You'll need to be able to use that and manipulate it and apply it for your quiz as well. And you'll need to be able to do problems using Charles's law. And that is it. That is it for the Chapter 14 review. Your Chapter 14 quiz, again, for the 1 millionth time, is this Thursday, which is not tomorrow, but the next day. The 20th of May in the year 2020. Then we will work on our final mix of chapters. We're going to see that we're going to take some parts from chapter 15, 16, and maybe 17. I haven't decided yet, but definitely from 15 and 16. We're going to take a couple parts from each of those chapters and apply it in as one for our last chapter quiz. And then we will have our final unit exam over chapter 14 and our mixed chapter, which is 15 and 16. Please, as usual, let me know if you have any questions. Hit that subscribe button, like button. Just kidding. That's what they always say. Anyway, I don't even know if you can subscribe to my YouTube channel. That's so weird to say. I do. I guess I have a TLC Miss Montgomery YouTube channel for TLC kids only. So, no, I was joking, though. That means nothing to me. Anyway, that is it. Have a good day. Let me know if you have any questions in the Google Classroom comments. And I will see you tomorrow. Not really see you, but you know what I mean. Bye.